Chris Helmerson. Chris has taken this PhD with MIT and worked for a long time, almost 20 years at least, in the United States, and now he came as an Australian person. He's working here in Monash in Melbourne.
Great. Okay, thank you very much. My name is Chris Helmerson. I'm a professor at Monash University in the School of Physics. And as was announced, I was formerly at the National Institute of Standards and Technology, which is in Gaithersburg, Maryland, working in the Laser Cooling and Tracking Group. And for a while, I was also a member of the Joint Quantum Institute, the joint institute between the University of Maryland and NIST. What I'm going to talk about are various techniques on laser manipulation of neutral atoms. These are techniques that were developed in a large part at NIST by the group that I worked in over the past 25 years or so. So one of the overriding themes of 20th century physics has been the control of atoms. Having such studies or control of atoms led basically to the development of quantum mechanics, which provided a better understanding of how the atom works, and hence better control of atoms. And this knowledge, of course, led to things like the development of the laser, which in turn can be used to make more detailed studies in manipulation of the motion of atoms. And of course, controlling the motional state of atoms has opened up a whole new avenues of research and studies, which hopefully I'll be able to describe to you. So let me just take a quick step back in history and start at the beginning. Let's start with the work of Zeeman back in the late 19th century. So Zeeman discovered that if he took an atom and he put it in a magnetic field, and he looked at the D line of the atom, so that the light coming out of the atoms, he saw a broadening of it. And so this effect, known as the Zeeman effect, results where if you put an atom in a field, because of the intrinsic spin of the atoms, you get a splitting of the energy levels. And what Zeeman discovered is that if you use circularly polarized light, you could actually excite certain transitions over other ones. This was pretty amazing for over 100 years ago. So this and subsequent theory and experiments sort of established the fact that you could exchange angular momentum between light and atoms. And of course, this was in the early days, just before quantum mechanics, so there's a lot of old pioneers of quantum mechanics in there. But the first experiment, I think, that really showed linear transfer of momentum to atoms was this work by Frisch back in 1933, where basically he had a sodium atomic beam. He took a sodium lamp, so a lamp that emits light that's resonant with the sodium atoms, and he shined it onto the atomic beam, and he saw a deflection of the beam, a very slight deflection. So here are two curves, one showing the position of the atomic beam without the presence of the light, and the other one with the presence of the light, where you can see a slight deflection. I believe that's just taking the difference between the two curves there. And so this could be regarded as one of the first experiments which actually demonstrated the transfer of momentum from light to atoms. There have been some earlier experiments by Lebedev and Nichols and Hall, which demonstrated radiation pressure on bigger objects, but I would pretty much consider Frisch's 1933 experiment as the first one that showed the effect on free atoms. Of course, not much really happened until the arrival of the laser, and this actually eventually led to the development of laser cooling. In the meantime, people actually learned how to control the internal state of the atoms. One of the giants in this field was Alfred Kastler, who realized that you could actually prepare atoms in pure internal states using this technique of optical pumping. And these experiments were done with lamps, where they would use lamps and polarizers, circular polarization, to take the atoms from one internal state and put them all into another internal state. But it wasn't until, again, the arrival of the laser that people actually had a coherent way to transfer atoms into these internal states and interact with the center of mass motion. So by now you've heard a lot of applications of optical forces in various realms. You've probably heard several lectures on optical forces from manipulating micron-sized objects. And this is a big field now. Last time I counted, there were over 200 groups in 20 countries. And it overlaps in many different areas of research: atomic physics, optical physics, molecular physics, and so on. But what I will primarily focus on is techniques for manipulating and coherently controlling the motion of individual atoms. And so here's a brief outline of my 4 lectures coming up. So the first lecture will be primarily on laser cooling and trapping techniques applied to neutral atoms. And then I'll move on, hopefully by the second lecture, onto Bose-Einstein Condensation, one of the real breakthroughs resulting from laser cooling and trapping, and discuss Bose-Einstein condensation and some aspects of it, like superfluidity. And then I'll move back and focus on using optical techniques to manipulate primarily Bose-Einstein condensates in a field called atom optics, where basically you interact with the atoms as if they were light waves, but they're actually in fact matter waves. And hopefully I'll have a chance to talk about some other applications that are coming up on the horizon that look pretty exciting for laser-cooled and trapped atoms. So here's a very, very brief history of laser cooling. Some ideas have been around for a while. Back in the 70s, I think, people started coming up with ideas. I think Kessler had one of the early ideas to build a refrigerator based on optical pumping of atoms. There were papers by Hensch and Shallow on using light to cool atoms down, and simultaneously a paper by Weinman and Daymelt on basically the same technique for trapped particles. And experiments actually started around the mid-70s in the ion trapping community. So they were among the first people to actually try to use lasers to cool particles and remove their thermal motion. The work on neutral atoms really started in the early 1980s, and this, of course, led to the 1997 Nobel Prize in Physics for Steve Chu and Bill Phillips and Claude Cohen-Tanucci. So despite all the early work that was done on ions, my lectures will primarily focus on neutral atoms. So let's start at the beginning. You may have already heard this, but it's probably worth repeating. What are the mechanical effects of light? So you're probably aware that light comes in quantized packets of energy called photons. In addition to carrying energy, the light can actually carry momentum, which is proportional to the energy. And if you can transfer this momentum to another object, you actually can produce a force on the object. So the force results from a redistribution of the photon momentum interacting with the object. So here's a simple example. I have an object, let's say an atom of mass m. A photon with momentum p comes in. Let's say the atom scatters, but backscatters the photon, so the photon's going off with momentum minus p. Then by conservation of momentum, the particle has to recoil and pick up momentum 2p. As a result, the particle, or the atom initially at rest, now has a velocity. There are basically 2 types of light forces that people use in neutral atom work. One called the radiation pressure or scattering force, and the other one's called the gradient force or the induced dipole force. So radiation pressure for atoms is due to the absorption of photon followed by radiation of the photon by spontaneous emission. So imagine I have a light beam coming from the right here. So here's my light beam incident on the atom. The atom will absorb a photon and get a kick due to the photon momentum, and then it'll re-radiate the photon in some direction and get another recoil kick in that process. But typically the atom, for many such absorption spontaneous emission cycles, will re-radiate the photon in a random direction. So on average, the re-radiated photon contributes no net momentum to the atom. So the net momentum actually comes from the incident light beam. So as a result, the atom, on average, will move off in this direction. And here's an image taken of a cloud of atoms, initially at rest. So this is a very, very cold cloud of atoms, initially at rest. I come with light from the right. The atom absorbs a photon from the beam, gets a kick, the momentum p, and then re-radiates in some random direction another photon momentum kick. And so as a result, the momentum of the atom has changed, and the atom will move to a new location sometime later. If I take a picture of the distribution of atoms after some time, I find that it lies on this circle here, because the atoms have gotten a kick, one momentum kick here, and then re-radiated in some direction. So by now you've learned that for bigger objects, you can often associate this radiation pressure force with reflection, for example, in optical tweezers work. The gradient force arises due to absorption followed by stimulated emission of photons, in contrast to spontaneous emission. So for example, let's say I have an atom sitting here. I shine two light beams, one from the left and one from the right. The atom will absorb a photon from one beam, let's say this beam over here, coming from from your left, or actually the other way. The atom will absorb a photon from this beam coming from the right, get a momentum kick, and then re-radiate, or be stimulated to emit a photon from the other beam into the other beam, and as a result, get another momentum kick. So in this process, the atom has gotten one kick from the absorption process, and another kick of momentum due to stimulated emission. And here you can see this in an image of a very cold cloud of atoms, which were initially at this location. The atoms absorb a photon and are stimulated to emit a photon. So they absorb a photon coming from the right and stimulate a photon going to the left. As a result, they pick up 2 units of photon momentum. And so the atom now with 2 units of photon momentum has moved to a new location. If I take a picture of the atoms, distribution of atoms sometime later, I find that it's moved off in some direction. And for bigger objects, you can often associate this force with refraction of light. For example, if you're trapping things with optical tweezers. So now let's consider in more detail the radiation pressure of a plane wave acting on an atom at rest. So let's consider a 2-level atom, which has a ground state and an excited state. The energy associated with this transition is given by this frequency, omega sub A, for the atom. Now, what I want to do is I want to shine on laser light at a frequency omega sub L with an intensity such that it produces a Rabi frequency of omega sub R here. So normally in this 2-level atom system, if you excite an atom to the excited state, it'll re-radiate the photon by spontaneous emission, where the excited state lifetime results in an emission rate given here by gamma. So you can actually do an analysis either using sort of a classical Lorentz model of an electron on a spring or more detailed 2-level calculation. And you find that the rate of scattering photons looks like this. It's given by this sort of Lorentzian form here, where the rate at which you can scatter photons excited by this laser, omega sub L, depends on the relative detuning between the laser and the atom, here given by omega sub L minus omega sub A, which we denote by little delta. And it's, for low intensity, it's just proportional to the light intensity, which goes like the square of the Rabi frequency. And the width for low intensity is just going to go like the line width, natural line width of the transition given by the spontaneous emission rate, gamma. So if I have a laser that's off resonance, and of course what you find is that the rate of photon absorption is decreased, and exactly on resonance, you find that you get the maximum emission rate, which for low intensity is basically proportional to the spontaneous emission rate. So now if I want to calculate what the force is acting on an atom, so consider an atom here being illuminated by a plane wave, in this case coming from the left. The force, the average force imparted to the atom will depend on the rate at which you're scattering photons times the amount of momentum transferred per scattering event. In this case, it's h bar k for each photon, momentum associated with each photon, times the photon scattering rate. So if I just plug this equation here, substituting in these other symbols, this is what I get for the average force acting on the atom as a function of the relative detuning from the excited state of the laser, capital delta. Now, to actually use this for something useful like laser cooling, we have to take into account the motion of the atoms. And so this requires us to consider the Doppler shift for resonant absorption. So this formula I gave here had nothing about the velocity of the atom. This considers just an atom, a 2-level atom without considering its motion. Now I want to consider what happens if the atom's moving. So imagine again I have my atom here with a frequency, transition frequency of omega sub A. The atom's moving with some velocity v and has mass m. So So I shine a photon at it, okay? And the process of absorbing the photon gives the atoms a kick. So the atom initially with velocity v has a momentum m times v and a kinetic energy 1/2 mv squared. After the absorption of the photon, it has a new velocity v prime corresponding to the change in momentum from this absorption process. So mv prime here. So by conservation of momentum, I have that the momentum change of the atom results from just the absorption of the photon momentum, h bar k here. And you can actually rewrite this in terms of new notation where you can assign a characteristic velocity associated with this momentum transfer from the photon for an atom of mass m. This is called the recoil velocity, v sub r here. In addition to momentum conservation, I have to consider energy conservation. So I have the laser at frequency omega L and the atom at frequency omega sub A. And the difference between the absorbed and between the light, the laser light and the absorption process has to be equal to the change in the energy, kinetic energy of the atoms from this process. And so if I just plug in the numbers here, what I get is that the relative detuning of laser now is equal to h bar times k dot v plus a term that goes like k dot v recoil. It goes like k squared here. So this term here is the Doppler shift. So this is the shift in the resonant frequency of the atom associated with the motion of the atom. And this term is called the recoil shift, and it's the change in energy of the atom associated with the absorption of the photon. So when you absorb it, the atom absorbs a photon, it of course moves, and as a result gets a recoil shift. And so that's what this shift is here. And so here's the actual formula. The tuning is now k dot v plus the energy, recoil energy divided by h bar in this case, because I'm considering just the frequency difference. Because the recoil shift doesn't depend on the atom's velocity, but it does depend on which atom you're working on, because it has the mass of the atoms in here. People tend to just lump this into the definition of the absorption, the resonant frequency of the atom. So you can absorb this recoil shift into the resonant frequency of the atom and define a new resonant frequency for the atom. And so the effective detuning for this process just goes like omega sub laser minus omega sub atom, which is now delta minus k dot v. So this is the effective detuning resulting from the motion of the atoms due to the Doppler shift. It's just the original detuning where you have to take into account that you actually lump the recoil shift into the atomic resonance frequency minus k dot v. So now I can put this into my equation describing what the average force is acting on the atom. And basically all you do is replace the detuning term in the original equation by this new term which contains the Doppler shift. And so now what I have is I have the average force acting on the atom as a function of the velocity of the atom. And so you can plug in some numbers, typical numbers here. For example, if you want to know what the maximum acceleration is, that occurs when you're at a detuning equal to the shift in the resonant frequency due to the Doppler shift. So when delta is equal to k dot v, or in other words, this term is 0, and you go to high intensity limits so that the scattering rate, you're at the maximum scattering rate of gamma over 2. And then you can compute what the average acceleration is just by taking the average force dividing it by the mass, and you come up with that that's equal to the photon, the recoil velocity, or the momentum of the photon divided by m, times the maximum scattering of gamma over 2. So as an example, let's look at a sodium atom. This is sodium 23, atomic mass 23. The recoil velocity associated with sodium. So sodium has a resonant excitation at 589 nanometers. So you can use that to compute what K is. And then put in the mass of the sodium atoms, and you find that the recoil velocity associated with the absorption of a 589 nanometer photon for sodium corresponds to 3 centimeters per second. And the maximum scattering rate of sodium is is given by the excited state lifetime, which is 16 nanoseconds. So you get a gamma here of 10 to the 7 inverse seconds. If you put these numbers into this equation, you find that the maximum acceleration you can impart to a sodium atom, if you're always on resonance, is 9 times 10 to the 5 meters per second squared. So this is a relatively high acceleration, or if you want, you could use it to decelerate an atom. And this force can basically stop a sodium atom moving at 1,000 meters per second in about half a meter. So to do this, you have to scatter roughly about 30,000 photons to do it, but you can do it. It's routinely done in the laboratory. So let's take a look again at the history of people using lasers to slow atoms. One of the earliest attempts to slow an atomic beam was in the former Soviet Union, in a group led by Lebedev, who's one of the pioneers in the field. This was done in the early 80s, and basically what they did is they took an atomic beam of sodium coming out, and they shined a laser, a counter-propagating laser beam. And what they saw is they actually changed the velocity distribution of the atom. So the dashed line here is the initial velocity distribution of the atoms coming out of this oven. And when they shined the laser on the thing, they actually shoved some of the atoms down to a lower velocity. And this is because the atoms absorb a photon from this beam, get a kick, and they're slowed down by the beam as they, after each absorption followed by spontaneous emission cycles. But what you see here is that after a while, you basically pile atoms up at a lower velocity, but you don't continue pushing atoms down to zero velocity. And the main problem is the Doppler shift. If I set this laser to a fixed frequency, the atoms that's resonant with sort of the peak velocity of the atoms coming in the atomic beam. After a while, those atoms that have slowed down due to the slowing laser, absorption of photons from the slowing laser, will actually Doppler shift out of resonance, and so they're less likely to scatter any more photons, and as a result, you get this pileup of atoms here. So after this initial demonstration, a number of groups looked into how they could continue this process. And one obvious solution is, what I want to do is, if I have the laser set to this frequency here, with slow atoms at this velocity, if I start piling atoms up at this lower velocity, then what I want to do is shift the laser to a new frequency so I act with this velocity and move it down, and so on. So using a process of shifting the laser frequency, I want to actually shove this velocity distribution to lower and lower velocity. And so one of the earliest techniques that people used for slowing atoms is called chirp slowing. And the basic idea of chirp slowing is you want to consider an atom moving with velocity v. Then you can look at any other velocity by transforming to another frame. Actually, let's do the opposite here. We want to go to a frame moving with velocity here, capital V. And so any velocity in that frame you can just get by this Galilean transformation. In the presence of the counter-propagating laser beam, you want to know what the acceleration is in this frame. And so in this process, you also want to chirp the laser. So as you're slowing the atoms down, you want to stay resonant in the particular frame of the slow atom. So as a result, your velocity of your reference frame is going to change as a function of time, because as you're decelerating the atoms with this deceleration A, then you want to shift to a new velocity frame given by the initial velocity frame plus A times t. And this is achieved, the slowing process is achieved by basically sweeping the laser frequency. So in other words, you're changing the velocity, the Doppler shift of the laser as you're slowing the beam. So if you plug all this into the equation, you find that in the decelerating frame of the atom, you have an equation for the average force acting on an atom with velocity v prime. So this is the velocity of an atom relative to this moving frame, capital V. And this is the average force acting on the atom due to the laser, but you also have this fictitious force because you're in this decelerating frame. Now if I ask what the average force is acting on the atom about this velocity, or I can expand about this velocity v prime about 0, and I find that the average force looks like this. And basically, if you expand it about v prime equal to 0, you find that it actually results in a damping force. So the average force acting on the atom in this moving frame looks like a damping force. If you choose a detuning such, this coefficient alpha here is negative. And so what this means is that if I'm decelerating atoms using this chirp slowing, not only am I interacting with a particular group of atoms and shoving them down to lower and lower velocities, I'm taking any atoms in the vicinity of this velocity in the chirp frame, and I'm actually piling atoms up around that velocity. So all velocities within a range around v prime are damped towards that velocity. And as the laser frequency is swept, you go to lower and lower velocities will come into resonance. And in addition, if the intensity changes with distance, you can always adjust, the velocity will adjust itself to always give you the constant acceleration that you desire in this process. So the only constraint to this is that you have to make sure that you don't sweep the laser frequency faster than you can actually decelerate the atoms. So as I mentioned, for sodium atoms, the maximum rate at which you can decelerate was on the order of about 10 to the 6 meters per second squared. And so this means that you can't chirp, for sodium atoms, you can't chirp the frequency much faster than, in this case, it's about 780 megahertz per millisecond. This is a relatively fast chirp, and you can still do this using electro-optic modulators, or you can actually sweep diode laser currents. So one of the first demonstrations of this was actually done in Bill Phillips' group by his first postdoc, John Croden, at the time in 1984. This is, I believe, data from I think this is from Bill's group. So here's the initial velocity of the atoms, and they initially put the laser on this frequency, but then swept the laser frequency down. And you can see that in contrast to the experiment of the group in the Soviet Union, former Soviet Union, and we just sort of piled atoms up at a slightly lower velocity. Here you've actually pushed the velocity of the atoms down to a much lower velocity. So you've made a very big gash in the velocity distribution, piling atoms at a lower velocity. An improved version of this experiment was done in Jan Hall's group in 1985. And one of the first demonstrations using chirp diode lasers was done in Carl Lyman's group back in 1986. So chirp cooling, it's a very robust technique. The only limitation is that it's inherently a pulse technique, because you set your laser to interact with one velocity group, and you follow that velocity group down towards, for example, zero velocity or close to zero velocity. And then you have to bring the laser back and find another group of atoms and bring it and slow them down and so on. So you chirp this laser beam, but you sort of repeatedly do this. As a result, you actually produce a slow beam of atoms coming out, but they're, in some sense, they're sort of pulses of slow atoms coming out of the slowing process. So at the time, Bill Phillips was looking at other ways to slow atoms, and he and Al Metcalf were considering a number of different techniques. And one of the techniques they came up with involved the Zeeman effect, which I mentioned earlier. So let's review what the Zeeman effect is. If I have an atom in a magnetic field, the atom has an intrinsic or internal angular momentum associated with either its spin or the spin of the nucleus, or some orbital angular momentum associated with the electron in the atom. So this is given by the quantum number F here. This gives rise to a magnetic moment in the atom, which is proportional to the intrinsic spin of the atom, or the intrinsic angular momentum of the atom. And so now if I put this magnetic atom with a magnetic moment in a magnetic field, this results in an energy here, given by mu dot B. In the Zeeman regime, it turns out that the energy is just proportional to the magnetic field, and depends on what the spin projection of the atom is along the direction of the magnetic field. So for example, in sodium, atoms in the ground state, 3s1/2 ground state, there are basically two hyperfine states. There's F equals 1, which has m equals -1, 0, and 1 sublevels, and F equals 2 with M equals -2, -1, 0, 1, and 2 magnetic sublevels. And the energy between these hyperfine states in sodium is split by about 1.77 gigahertz. But if I apply an external magnetic field, and in the presence of this magnetic field, you get the splitting of these magnetic sublevels within a particular hyperfine manifold. So in the lower hyperfine manifold, which has an opposite G factor to this one, opposite sign G factor, you find that the M equals +1 state goes down with it in energy as a function of magnetic field. The 0 state, M equals 0 state here, if you look at this equation, has no shift in the Zeeman regime due to interaction with the magnetic field. And the -1 state goes up. And up here you find the opposite, M equals +2, has twice the interaction energy compared to +1, so it rises twice as fast. Now you can apply, you can use the fact that the energy levels of the atoms are changing as a function of magnetic field to actually keep the atoms on resonance during the slowing process, rather than chirping the laser. And this is the basic idea behind what's called Zeeman slowing for atoms. So in Zeeman slowing, rather than chirping the laser frequency to always keep in resonance with a particular velocity group, what I want to do here is make the resonant frequency of the atom shift as it's slowing down. Now, as an atom's slowing down, it's also moving. So all you have to do is make the resonant frequency change as a function of position, so that when as an atom slows down and moves to a new place, it comes in resonance again with the laser. And so if you have a deceleration rate that you're trying to achieve of A here, just by conservation of energy, you can find out that if you have atoms with an initial velocity v sub 0, then the new velocity at location z, as the atoms are decelerating at a rate A, with deceleration A, then the velocity at a position z will just be given by this equation here. So it looks like an inverted parabola. And so all you want to do is make sure that you choose a magnetic field such that, a magnetic field profile such that the Doppler shift of the slowed atom is compensated by a change in the magnetic energy, the energy level of the atoms due to the presence of the magnetic field. And so just by equating these the Doppler shift, the shift in energy associated with the Zeeman shift, you find that basically you want a magnetic field profile that looks like this inverted parabola here. So there's some constant, often people put some sort of bias field on the system, but basically you have this inverted parabola. So an atom initially at one location will slow down, and so this is the field profile that corresponds to constant deceleration of the atom. Typically, the way you do this is you have your atomic beam down here, you have this counter-propagating slowing laser at some fixed detuning, and then you build a magnetic field profile such that it's strongest at one end and weaker at the other end. So it's often called a tapered magnetic field. So here's an example of some early data from Bill Phillips' group back in, I think, 1983 or so, where he used Zeeman slowing to slow atoms down. This is a schematic of the setup, I believe. But anyway, if you look at this, this is the initial distribution of the atoms, this dashed curve here. And this is the final distribution of atoms, this solid curve, due to the presence of the Zeeman slower. So here, in this case, you keep the laser at a fixed frequency, but as the atoms move in this tapered magnetic field, in this spatially varying magnetic field, they come back into resonance with the laser, and as a result, scatter more photons and get slowed down to lower velocity. So the nice thing about Zeeman slowing is it actually produces a continuous beam from atoms, because the atoms coming through this process is continuous, the laser stays at a fixed frequency, and as the atoms move through the magnetic field, they get slowed down and come out with some final velocity, in this case around 600 meters per second or so. So this is one of the standard techniques that people use for slowing atoms. And so for example, is the technique that I used extensively when I was at NIST for slowing atoms. So once you have atoms that are slow, then what you'd really like to do is capture these atoms and cool them to even lower temperatures. And so let's revisit the issue of radiation pressure or light acting on atoms. But in this case, instead of just a unidirectional laser beam coming from one direction, let's consider laser beams coming from two different directions, so counter-propagating laser beams. So just to remind you, the radiation pressure from a plane wave, so just one laser beam, we found was given by this equation. So the average force acting on an atom due to one laser beam is given by this equation, including the Doppler shift. If I just consider the case where I go to low intensity, so I can neglect this intensity term due to power broadening in the denominator here. This is the average force acting on the atom due to the presence of one laser beam. Now let's consider two counter-propagating laser beams in a configuration that looks something like this. Basically, what you now want to do is consider the average force, and you assume that there's no sort of correlation between the two laser beams, so there's no, if you like, stimulated emission process where you absorb a photon from one beam and stimulate it to emit another one. So these are two independent scattering processes. Then I have the average force acting on the atom depends on the force due to one laser beam moving in one direction, in the minus k direction, and the force due to the other laser beam moving in the plus k direction. And of course, because of the k vectors change here, you see that there's also a change in the Doppler shift of the atom c. So an atom moving with velocity v will see the Doppler shift going one way from one laser beam, but it'll see the opposite Doppler shift for the other way. So if I take this equation, I expand it for small velocities, and look to see what I get. The average force acting on the atom in this case is given by this equation, and again, it turns out to be, for small velocities, just to be proportional to the velocity. So what this tells us that is, if I actually choose a detuning such that this coefficient here, alpha, is negative, then what I have is that the average force acting on an atom due to two counter-propagating beams actually creates a damping force. We saw this expression earlier when we considered the chirp slowing in a moving frame, that it also produced a similar type of damping force, except in that case we only had one beam, so it was only proportional to the intensity. In this case, because we have two beams, it goes like the intensity is twice as large. So this is what the profile looks like as a function of velocity if you look at this equation here. Again, for small velocities, you see that it's basically proportional to the velocity. So, oops, I forgot to put axes on here, but this is force as a function of velocity of the atoms, and this corresponds to zero velocity. So as the atom moves to some velocity, what it does is it feels a net force pushing it back towards zero velocity in this regime. Of course, if the velocity is too large, then what happens is this equation no longer holds, and it turns out that the force just falls off if the velocity is too large. So you get this curve here. If you look at the green curve and the red curve, these are the individual forces from each one of these contributions to the cooling force. So this shows us that we can actually generate a damping force on an atom by using two counter-propagating laser beams. And these ideas were first suggested by, back in 1975 by Hench and Shallow, who considered basically this geometry, and Wineland and Daybell, who considered a geometry corresponding to a trapped ion. Now, the only thing we've sort of neglected in the discussion of the damping force is the momentum diffusion due to spontaneous emission. So this damping force is provided by the absorption of a photon, giving you a kick, and you choose the detuning such that you preferentially absorb a photon from a counter-propagating laser beam, which kicks your velocity back and tries to slow you down. But each one of these absorption processes has to be followed by a spontaneous emission process in a random direction. And what that results in is a momentum diffusion of the atoms due to this random emission of photons in some direction. So, as I said, each emission process gives a momentum kick. And if you assume that it's uncorrelated from absorption, from each absorption process, the emitted photon is uncorrelated, then you can write down an equation for the momentum diffusion coefficient. So here I consider the momentum diffusion coefficient as d sub p. And that's basically going to be the diffusion of the momentum, which I can calculate as the rate at which you're scattering photons from each of these absorption processes, times sort of the average momentum squared due to re-emission of the photons. In this case, it goes like h bar k squared. So I already know what the equation is for R that was given earlier for the absorption process, and I plug that in here. And so the net diffusion coefficient is given by this equation. If you want to know what the heating rate due to this diffusion coefficient is, then you just take the diffusion coefficient divided by the mass. And then we have that the cooling rate just depends on the average force times the velocity, so it goes like minus alpha v squared. So how cold can you actually cool it, or how low you can actually cool the atoms to, or how low temperature you can cool the atoms to, depends on the competition between the rate at which you're cooling the atom against the rate at which you're actually heating the atoms up due to this random diffusion of the atom in momentum space due to spontaneous emission of photons. And so if you equate the two, you can find that in steady state, you have that the cooling rate is equal to the heating rate. And so by looking at the steady state situation and plugging in the numbers for the diffusion coefficient and also for the diffusion coefficient here, you find that the average velocity or the average kinetic energy of the atom is going to be proportional to the diffusion coefficient divided by the damping rate. And you can equate this average velocity of the atoms that you cool to a temperature just by the equipetition theorem. And if I plug in what my calculation earlier, the diffusion coefficient, this is what I get for the final temperature of the atoms due to this, in a standing or due to two counterpropagating laser beams as a function of the detuning of the laser for the atomic transition. So you can plot this, and this is, you get a curve that looks like something like this. There's actually a minimum in this equation here, and you find that the minimum occurs when you choose a detuning that's equal to exactly half a line width off resonant. And at that minimum point, you get a temperature that corresponds to, from this equation, is equal to h bar times half the natural line width. So this result was derived by Wyman and Nakano in a paper on laser cooling of atoms and ions back in 1979. And it's valid as long as you can neglect the sort of the recoil energy of the atom, or if that energy is small compared to this, the resulting final temperature. Otherwise, what happens is you always have this random emission process, and so if you try to go lower than that, in some sense you can, and so you're always limited by this random emission process, always ending up with something on the order of the recoil energy is the final temperature of the atom. So the amazing thing about this is it basically only depends on one atomic parameter, just the excited state line width, no other parameter. So if I look at some typical atoms, in this case sodium, which has a natural line width, or an excited state lifetime of 16 nanoseconds, so gamma here is about 10 to the 7 in 2 seconds, I find that the final temperature I can cool atoms to using two counterpropagating laser beams is on the order of 240 microkelvin. If I look at what the recoil energy associated with the absorption of a photon is, I find that it's on the order of 1.2 microkelvin, so that's much less than 240. So this Doppler cooling limit temperature should be valid. In the case of cesium, which has a natural line width that's half the value of sodium, you can cool using this technique of Doppler cooling to 125 Cesium's got a much heavier mass, slightly longer excitation wavelength, so the recoil energy here is even smaller. So after this, this was shown back in this paper in 1979, and there were some subsequent papers doing similar type calculations which confirmed it. But the first experiment to actually demonstrate this sort of Doppler cooling is something that was coined optical molasses by Steve Chu and collaborators at Bell Labs. And basically what they did is they set up 6 laser beams, so 3 pairs of counter-propagating laser beams along, for example, the principal axes, it's at X, Y, and Z. They chose a detuning to be equal to the detuning that you would want to get the maximum cooling. So they chose a detuning of exactly half a line width for low resonance. And they actually loaded atoms into this region of the intersecting laser beams using chirp slowing in their case. And they were working with sodium atoms. And what they found is that basically they cooled atoms to a temperature that was on the order of the Doppler temperature predicted as 240 microkelvin. But they had fairly big error bars because the way they measured temperature back then is they basically shut off these laser beams, and the cloud, which has at this non-zero temperature, will start expanding out. And then you just turn on the laser beams again and look to see what the number of atoms are in a certain region. But using this method they call release and recapture, they found that the temperature of their atoms was on the order of about 240 microkelvin, which agreed well with theory. And here's actually a picture of optical molasses. This is not from Chu's experiment, but it's actually from the apparatus I used at NIST, showing where here you can kind of see the intersecting laser beams due to background vapor in the system. But this bright ball in the middle corresponds to the atoms that are slowed down using this optical molasses or Doppler cooling. Yes? Sorry? Oh, sorry. Okay. It's time to take a break then? Yeah. Okay. Well, this brings us to an exciting point, and so we'll come back to do that. All right. Thanks.
Okay, questions? Yes.
So, is the effect of the re-emitted photons on other atoms, is it negligible?
At the densities these experiments were done, yes, but at higher densities.
At a higher density,
it becomes an issue, and reabsorption is a problem. And I'll mention that later when I talk about Bose-Einstein condensation. It's one of the major reasons that people can't actually get the Bose-Einstein condensation using only laser cooling.
Any other questions? Okay, so let's take a break.